Hello, my name is Chris Morton. I'm a testing engineer here at PowerTech Labs in Surrey, British Columbia. PowerTech performs third-party testing and consulting services for the electrical industry. PowerTech was contracted by the International Copper Association to perform a study to compare the connectability of copper and B8000 series aluminum alloy wiring. Test samples consisting of lengths of wire and electrical connectors were subjected to accelerated aging by electrical current cycling. For the study, PowerTech determined a suitable test program that was based on the standards ANSI C119.4 and IEC 61238-1. The test program involved current cycling at elevated temperatures and in a high humidity environment. Also included was a single short circuit test as per the IEC standard. This test program was chosen to produce conditions more severe than the standard ANSI test, also to observe and record failures. Test samples were prepared per the ANSI standard and consisted of a length of bare wire, an electrical connector, and a current equalizer. All wire and connectors used in the study were off-the-shelf components and were obtained from local equipment suppliers. The wire used for the samples was number 1 AWG copper and number 2-aught AWG B8000 series aluminum alloy. These sizes are of approximate equivalent ampacity. The electrical connectors used in the study were mechanical single-screw, single-hole terminal lugs. Both copper and dual-rated aluminum connectors were used. The variables for installing the connectors were the torque level applied to the set screw, wire brushing of the conductor, and the use of oxide inhibitor. Each connector type was installed at 3 torque levels, 70%, 100%, and 125% of manufacturer's rated torque. This was to produce a range that would be expected in service. Connectors were installed on copper wire samples with no wire brushing and no oxide inhibitor. Aluminum wire samples were installed with and without wire brushing, also with and without oxide inhibitor. This table shows a summary of the sample types and preparation methods. Current equalizers were installed on the end of each test sample. A current equalizer consists of a conductive bar that is welded to all strands at the end of the conductor. This is a standard technique and ensures the best possible connection to the end of the conductor. Control samples were also prepared, which consisted of lengths of conductor with equalizers but no connector. The test samples were connected together in a series circuit as shown in the diagram, so the same current level could be passed through all samples simultaneously. During testing, the current was automatically regulated at a fixed level and the temperature of each connection was measured using thermocouples. Each current cycle was 2¼ hours long and consisted of heating the samples to temperature stability at a constant current level, followed by a cooling period back to room temperature. A total of 1,500 current cycles were performed for the test. Resistance and temperature values were recorded throughout the test and were evaluated at 1,000 and 1,500 cycles. This chart shows an evaluation of the resistance after 1,000 cycles using the method from the IEC standard. Each vertical bar represents one test sample. The height of each bar is the ratio of resistance at 1,000 cycles compared to the resistance at the start of the test. The line at the ratio of 2 indicates the maximum allowable ratio according to the IEC standard. A resistance ratio above this line is considered a failure according to IEC. Samples are grouped by wire and connector type, with each color representing one group. The purple tinted bars are samples made from copper wire with dual-rated aluminum connectors. The orange tinted bars are samples made from copper wire and copper connectors. The blue tinted bars are samples made from aluminum alloy wire with aluminum connectors. As we see from the chart, the samples that use copper wire and aluminum connectors have some resistance ratios below the limit and some above the limit. The samples with copper wire and copper connectors are all below the limit, and the samples with aluminum wire and aluminum connectors are mostly above the limit. This chart shows an evaluation of the temperature after 1,000 cycles using the method from the IEC standard. The height of each bar is the maximum temperature difference between the sample and the control conductor throughout the test. According to the IEC standard, the temperature of the sample is not allowed to exceed the temperature of the control conductor. A temperature difference greater than 0 is considered a failure according to IEC. The height of each bar indicates the maximum temperature difference between each sample and the control conductor. And again, the samples are grouped by color according to the sample preparation and type. Samples that are below the 0 line indicate a sample that is run cooler than the control conductor, and those above the 0 line have run hotter than the control conductor. A temperature difference greater than 0 is considered a failure according to IEC. As we can see, the samples with copper wire with aluminum connectors have some that are below the control temperature and some that are above. The copper wire samples with copper connectors have the majority that are below the control temperature with a few that are slightly above. With the aluminum wire with aluminum connectors, we have the majority of the samples that are well above the control temperature. Here we see in this chart, again, we have the temperature difference between the sample temperature and the control, except in this case, this is the final value after the 1500 cycle test is complete. So here we see the majority of the samples that had copper wire with dual-rated aluminum connectors are below the zero line, and all of the samples of the copper wire with copper connectors are below the zero line. And the majority of the samples that had aluminum wire with aluminum connectors are well above the line. To conclude, we saw the best performance in this study with the copper wire and the copper connectors. The next best performance was with the copper wire and the dual-rated aluminum connectors. And lastly, the poorest performance was with aluminum wire and aluminum dual-rated connectors. Also, we saw no strong correlation between the sample preparation and the performance of the aluminum wire and aluminum connectors. A full report for this study may be obtained at copper.org.